For today, we will finish chapter 3 on the general equation. I will go briefly, very briefly, to chapter 5, and we will skip chapter 4. Okay, we will go through chapter 5 very quickly, and hopefully we can be halfway in chapter 6. Okay. This is last example for chapter 3. Of course, there are a lot more in the textbook. I would encourage you to study the example by yourself. In the textbook, there is no detail on the dropping of the terms. Okay, they just set it up and give you the solution at the end. So you have to work on your own a bit. The example for today is a tank. It's a cylindrical tank like this. Okay, and at the center there's a shaft. It seems like an annular flow, but actually it is a tank. Water is filled in the tank, and the tank itself is rotating. You can rotate the tank. Just like when you do the bakery, you put mixture in the bowl and you rotate the bowl, something like that. In this example, this shaft is stationary. The tank itself is rotating. So therefore, at the end, at the bottom, this shaft is not connected to the bottom of the tank. Okay? So the system is fluid, is liquid in the annular area. The angular rotation velocity of the tank is omega 0. That's angular velocity. The radius is r. Inside diameter is kr, so k is less than 1. We want to find velocity profile. Again, the first step is basically pick the coordinate, assign the origin point. This looks like cylindrical coordinate, right? So we will pick cylindrical coordinate. This is z. One axis supposed to go along with the flow. The flow is in theta direction. So theta is going this way, z is going up or going down, doesn't matter. And you have r going from the center. This is r. Okay? The second step, identifying velocity components. In this case, let me write down here. We have VR, V theta, Vz. Which one is 0? Do we have VR? So if there's VR, the fluid is supposed to go in this direction, either going out or going in. Is there any such flow? No, not in this case. So VR is 0. Is there any V theta? It's rotating, so therefore, at solid interface, this fluid is supposed to travel with the same velocity as a fluid. It's go this way. At this interface, velocity of liquid is 0. It's solid-liquid interface. So if you draw a dotted line, you see that velocity here and velocity over there are not the same. So there are velocity gradients. Okay? So in this case, V theta is not 0. Obviously, it goes this way. Right? Vz, is it 0? Liquid is filled in the tank. Does it move up and down? No. In this case, Vz is 0. all right? Then you have to analyze Vz and V zeta, whether it is function of R, zeta, or Z. Is V zeta a function of R? Again, look at this picture. Is this dotted line? It goes in R direction. V zeta here is 0. V zeta here is not 0. So at least there are 2 points that give you velocity distribution in R direction. Okay? So V zeta is a function of R for sure. Is it function of zeta? So that means going around this circle, does it change? So if you have to imagine if it does change, let's say it's going faster, it cannot come back to original point. So with the symmetry picture like this, there's no way that V zeta would be a function of zeta. So it is not function of zeta. Okay? What about Z? Is it function of Z? Now, if you consider the whole system, then this is going in Z direction. This is V zeta going in this rotating direction. So this is V zeta at large Z. V zeta at bottom, are they the same? If you think that the bottom plate also rotates with the tank, then would they be the same? If the bottom does not rotate with the tank, then they're different, right? If the bottom does not rotate with the tank, velocity here and velocity there are not the same. In that case, it is function of Z. So in order to avoid the complication of the problem, let us focus liquid here. Just ignore the bottom, ignore the top. Just look at the uniform section. In that case, we can assume that it is not function of Z. All right? Now, once you already determine the non-zero component of velocity and determine its function, next step, as I said, when you do the momentum problem, if the system is pure species, okay, isothermal, then it would be suggestive to start with equation of continuity. This is equation of continuity in cylindrical coordinate, okay, without assumption of incompressible fluid. This is generic form. If you start with generic form, you can just eliminate terms that are 0. For instance, steady state term, this term will be 0. VR is 0 here. V zeta is not 0. It must be kept. Vz is 0. Okay? Under assumption of incompressible fluid, density is not function of position. So you can take this density out from the derivative. Then what you will get will basically dv zeta by zeta equal to 0. In other words, V zeta is not function of zeta itself. Okay? Then you start with Navier-Stokes equation. In order to use these 3 equations, you have to already assume, constant density and constant viscosity before you can use these 3 equations. Remember, Navier-Stokes equations are applicable only for incompressible fluid. Okay? Not only is incompressible, it must be Newtonian fluid as well. Now, 3 components. Let's start with the first one, steady state assumption, the first term is 0, it's not function of t. VR itself is 0, so it's 0 here, 0 there. We say that it's not 0, so therefore it must be kept. So this term would be kept. Pressure. How about pressure? Do we have pressure in R direction? If you do not know, if you are not sure, keep it for a while. Okay? Just eliminate the terms that are absolutely 0 first. And then we deal with the complication of the equation later. Now, moving on to this term, VR 0, 0 there, 0 there. V theta, this is V theta. In cylindrical coordinates, it might appear like this. You have V theta in our equation. That's normal. All right? The whole term, V theta by D theta here, it is 0 according to what we found earlier from equation of continuity. Or you can say that V theta is not function of theta from analysis of the problems, and you end up with eliminating the whole term. All right? Is there any gravity in R direction? Think about this. You're rotating. Is there any gravity in R direction? Don't be confused, okay? Don't be confused. Some of you might have a perception that when you rotate like this, there's centrifugal force. But this term is external force. If you think carefully, whatever you have in your mind about centrifugal force, that depends on rotation speed, right? So that depends on the fluid. But this term is supposed to be external force independent from the fluid. So, is there any external force in R direction? No, there are not. So this term is 0. Okay? So from our equation, what you will have would be these two terms, pressure and V theta by over R. So if I write it down, you will have rho V theta squared over R equal to dP by dR. Okay? Minus sign here and minus sign there cancel out. So this is what you will get from our equation. From this, you see that there will be pressure gradient in R direction. In other words, pressure gradient depends on how fast you spin, right? The faster you spin, the larger the pressure gradient. And I said, it is not pressure itself, it's a pressure gradient. This is change with respect to R. The larger the velocity V theta, the larger the pressure gradient. That is an effect that you call centrifugal force. Okay? For theta components, steady state assumption, VR here is 0. V theta is not function of theta, or according to equation of continuity, the whole term here is 0. Vc is 0. VR here is 0. So left-hand side turns to be 0. Right-hand side, do we have pressure gradient in theta directions? Does pressure change with respect to angle? Let me ask you this. It rotates like this. The flow goes in this direction. Does it mean pressure changing in angle? No, it does not. Okay? So pressure does not change with respect to angle. This term will be dropped. The whole term will be dropped. We say that it's not zero. It is function of R. So this differentiation is not zero. It must be kept. So let me highlight this term. This term must be kept. This term, on the other hand, according to equation of continuity, it is 0. Is V zeta a function of Z? As long as we ignore the bottom, the whole term is 0. Okay? What about this term? VR itself is 0. It's gone. No gravity in angular direction. So what we will have here is only one term equal to 0. So mu dV by d r 1 over r d by dr rv zeta equal to 0. Okay, this is zeta equation. For Z, steady state assumption, the first term is gone. Vi is 0. Vz is 0. So these two terms are eliminated. Is there any pressure gradient in Z direction? Go this way in Z direction. Do you have a pressure change? You do. Lower the depth, higher the pressure because of the head of water on top of it, right? So pressure is a function of Z. This term must be kept. All right? Vz is 0. All terms containing Vz will be gone. Gravity, do we have gravity in Z direction? You do. So this term is not 0. So if you write the equation for Z direction, you will have dP by dZ equal to rho gz. In this case, if I point the z-axis going up, gz would be negative g. But I keep gc in general, okay? I have not replaced this as gravity yet. Just keep it as gz. So this is z equation. But if you assign z going down, if you assign like this, z, r, then the gz here becomes g. Okay? Any question regarding all these eliminations? All right, so let me remove this. Now, if you analyze the equations, let me clear it a bit. All right? So from 3 dimensions of Navier-Stokes equation, you have R equation, theta equation, Z equation. Okay? From these 3 equations, you can see that in order to find velocity profile, Z equation is useless. It does not contain any velocity component. This equation gives you pressure profile. So we ignore this for the moment. Okay? Only 2 equations contain velocity. V theta here and there. Which of these 2 equations is useful for us to find velocity profile? Top or bottom? Seems to you sometimes that top would be easier because you don't need integration of V theta. Okay? But if you look closely, in order to solve for V theta from this equation, you need to integrate pressure. But pressure is a function of 2 variables. Pressure is a function of R and Z. So integrating pressure would be difficult. Okay? Instead, if you pick this equation, all you have to do is integrating twice. You get V theta. On the right-hand side, it is 0. So the first integration gives you just a constant. The second integration is straightforward. So using this equation would be easier to find V theta. So I'm going to pick this one, mu. And V theta itself is a function of R only. So I can replace partial differentiation by total differentiation. So I will have this instead. Okay? First integration, this term will be eliminated because the right-hand side is 0. You don't have to worry about mu anymore. Move it to this side, it turns to be 0. First integration, you have whatever inside. That would equal to a constant. Let's call it C1. Move R to the right-hand side and integrate it again. You have R V theta, whatever inside this integration. R from here goes to the right-hand side. When you integrate it, it turns to be R squared over 2. And then you need another constant, C2. Okay? So divide the whole equation by R. You get V theta equal to C1 R over 2 plus C2 over R. Straightforward. And you have to notice that after the first integration, in the previous examples, I apply boundary condition here to find C1 first before integration into the next step. But in this particular example, I integrated right away, twice. Why? Basically, if you integrate it right away, you end up with equation containing 2 constants. In this case, we need 2 boundary conditions in the respect of velocity. You have to ask yourself, do you know 2 positions? Do you know velocity in 2 positions? In that picture, we do know. But if I want to find this C1 at this stage, I need to know this, the whole term, which is somewhat a function of shear stress. We do not know shear stress at this point, so it is a little bit hard to apply boundary condition here. Okay? So at this stage, if you do not know any boundary associated with shear stress, I would suggest you to go ahead and integrate it further, and you end up with velocity equation with velocity. Finding boundary condition with velocity would be much easier. Okay? So from here, I need 2 boundary conditions. The boundary would be at R equal to KR, which is inside here, because this rod is stationary, and therefore velocity at this interface is supposed to be 0. Okay? So I know that at r equal to kr, v theta is 0. Also, at r equal to capital R, that's outside. Okay? At this point, is v theta equal to omega 0? Now, don't be confused. This omega 0 is angular velocity. It is angular velocity. But this v theta is linear velocity. They are not the same. In order to convert angular velocity into linear velocity, you just multiply by the arm distance. Okay? So at r equal to capital R, v theta is basically omega 0 times r. All right? From these two boundary conditions, plug it back in here, you can get C1 and C2. You can solve for C1 and C2, then you end up with velocity profile. At the end, you get v theta equal to omega r over 1 over k minus k r over kr minus kr over r. All right? This would be the answer for velocity profile. From here to there is basically a mathematics problem, and I do not want to spend time on it. I'm sure that you can do it by yourself. All right. Any question? Now, a little bit more. We already used this equation, so I can erase this equation. It gives you the velocity profile. What about these two equations? It has pressure, they have pressure in it. So if I want to find pressure gradient within the system, I need these two equations. Okay? I know that in the system, pressure depends on R and Z. It depends on R here because this side is not 0. It depends on Z here. According to, if I write it down like this, it would be very similar to what I use frequently in thermodynamics, right? So if I differentiate it, you get dP by dr, dr plus dP by dz, dz. Seem familiar? This one has been used so many times in thermodynamics. Okay? And we know that this is here, and that is here. Okay? So if I write further, I can get dP equal to rho v theta squared over r dr plus rho gz dz. That should be one single equation giving you pressure at any point. If you integrate this equation, you end up with pressure profile. Okay? Of course, in order to integrate this equation, you need to bring velocity profile here, replace in here. So this v theta is essentially a function of r. is essentially a complicated function of r. If you plug this v theta here, square it, and then integrate it with respect to r, eventually you get pressure profile. All right? I can show you how to do it, but, I don't want to do the complicated one, so I will simplify the equation or simplify the system a little bit. What if I change the system from a tank with a rod in the middle, if I change it to a tank without the rod? If I remove this rod, it means that in this system, K is equal to 0, right? No rod, K is 0. The tank is still rotating. You rotate the tank. There's a liquid inside, okay? Usually, when you rotate the tank, what you see is the liquid would go like this. The surface of the liquid turns to be curved, okay? If this is z-axis, so if I call this point the bottom point, z0, okay? And the radius is r. Can I use the equation that we derived earlier for that example? For K equal to 0, can I use this equation right away? Do we need to derive the whole thing all over again? In theory, you should be able to use this one, just applying K equal to 0 into the equation without deriving the whole Navier-Stokes equation again. In practice, you see that when I replace K equal to 0 here, you have problems. Okay? So I need to do something with this equation first. So from V theta equal to omega 0 r 1 over K minus K r over KR minus KR over R. Okay? If I take this K to here, at the bottom, I get 1 minus K squared. Okay? Over K, I take K up here. I can do that. And omega 0 R remains the same. Okay? In this part, I can take 1 over K out. Then I have R over capital R subtracted by K squared capital R over R. I can do that. And this K and that K cancel out. Then I can apply K equal to 0 without any problem. Okay? If K equal to 0, then this term will be 0. The whole term here will be 0. What I have left would capital R here and cancel capital R over there. Then I will get omega 0 R, which is basic conversion from angular velocity to linear velocity. So that means my equation is supposed to be correct. Okay? Without the middle rod, it follows simple physics. Okay? So if I plug this in here, then I end up with dP equal to rho v square, which is omega square r square over r. You get one single r dr plus rho gz dz. Now I can integrate to find pressure, integrated with respect to r, assuming constant density, constant angular velocity, that would be r squared over 2. Integration of this side, you get rho gz, right? And after integration, you end up with, after you integration this part, you get one integration constant. When you integrated this part, you get another constant. These two constants can be combined into one single constant. Okay? Now, to find this constant, I need boundary condition. The boundary condition that I would use is basically at this bottom point. Okay? But you have to realize that this equation, in order to find C, you need to know pressure at some point. But the point that you identify pressure, you have to specify both R and G. I'm sorry, R and Z. Okay? So in this case, my boundary condition would be at R equal to 0 and Z equal to Z0. That means I pinpoint this point. Okay? What is the pressure over there? It's at the surface, so pressure is atmospheric. So we know that pressure is P0, or atmospheric pressure. Plug it back in here, you get P0 equal to rho omega square times 0. So basically the first term is 0 plus rho g z0 plus c. So that means constants can be found, right? So c here is pressure, atmospheric pressure subtracted by this term. Okay? So once you know c, you take this c back here, you end up with pressure subtracted by pressure 0 equal to, in this case, it means that C equal to P0 subtracted by rho G Z0. Okay? Take this up here. So here you have P0. If I take P0 to the left-hand side, I end up with pressure subtracted by P0 equal to rho omega square r square over 2 minus, you have rho g as a common term. I can take it out. Inside, if I take Z0 first, I get Z0 subtracted by Z. Right? This would be your pressure profile. Or you can say, yeah, it gives you pressure at different spots in your system. Okay? Now, if I want to find an equation to represent this curvature. We know that the faster you spin, the more nonlinear this curve becomes. Okay? If you spin it slowly, it seems to be linear, seems to be flat. If I want to find this curve as a function of spinning velocity, I can find it from this equation. Okay? Notice that along this line, pressure is P0 everywhere, right? So if I said that I want to consider surface of the liquid only, that means at the surface, what we know, pressure would always be pressure 0. Okay? So if I pick this equation, apply pressure to be P0, the left-hand side turns to be 0. Right-hand side, you have the same thing. Oh, it's supposed to be R, not R squared. I'm sorry. Oh, I'm sorry. R squared, you need to integrate it. Get R squared. R squared over 2. Right? And then minus rho gz, z0 subtracted by z. So if I move z0 to the left-hand side, I will get z0 subtracted by z equal to, rho will be eliminated from the equation. You can divide rho for the whole equation. R squared over 2g, right? This should give you z as a function of r. So it gives you profile of this red line. That r or z depends on r. And the change of z and r depends on angular velocity. Okay? The higher the angular velocity, the more parabolic this curve will become. So this is a profile of the surface of the liquid. Okay, any question? So that's the end of chapter 3. As I said, there are a couple more examples in the text. Please try to do it yourself. Okay? Let me review it again. We start from chapter 1. That's an introduction of momentum transport and introduction of Newton's law. The purpose of Newton's law is a connection between what is transfer, which is tau, to what you can measure, which is velocity. Okay? The only equation that you have learned, linking between these two is Newton's law. That's in chapter 1. For chapter 2, we apply the Newton law to shell balance, introduce how to do the shell balance. If you integrate what you obtain from shell balance, you get velocity profile, right? Chapter 3 is an advancement from shell balance to make the shell more generic to develop equations that can be used for any problems. All chapter 1, 2, 3 still focus on laminar flow. You have learned in unit operation 1 that there are two kinds of flow, laminar flow and turbulent flow, okay? Chapter 4 in the text is basically laminar flow with the velocity that is function of more than one variable. So far, all examples that we have shown you are example that velocity is a function of only single variable, okay? In chapter 4, velocity is now more function of more than one variable. It can vary with two positions, two, let's say r or theta, x or y, and so on, or even r and time. So the essence of chapter 4 is basically math. And there's no point talking about math in this course, so I'm going to skip chapter 4. Chapter 5 is the introduction of turbulent flow. Okay, I'm going to go through it quickly so that I just want you to realize what is the difference between laminar flow and turbulent flow. If I ask the question, what is the difference between laminar flow and turbulent flow, I guess that almost everybody would say something about Reynolds number, right? If I limit my question, can you tell the difference between laminar flow and turbulent flow without talking about Reynolds number? What would be your answer? Now you will discuss something about turbulence. Now let me ask you this. If the flow in my system goes this way, like this, if it goes like this, is this considered turbulent? Or is this considered as laminar? The word turbulent in your mind, you have to be clear that it's, I know that it is clear in your mind that the word turbulent means the streamline is not linear, it's not constant, okay? But I want to be clear that the term constant is not limited to the constant with respect to position. You may have swirling, but still being laminar. It doesn't mean turbulent would always be swirling, okay? The term turbulent means that velocity is a function of time. But wait a minute, what about steady state? Can we have steady state turbulent flow? In our mind, the term steady state means it is not function of time. But as I said earlier, turbulent means it's change with respect to time. Can we have turbulent flow at steady state? The answer is yes, you can. The word that I said that turbulent flow is a function of time is essentially if you plot velocity with respect to time. Let's say you have a pipe, you measure velocity at one single point. If it is laminar, the graph is supposed to be like this, right? Laminar at steady state. At one single point, velocity is supposed to be constant. Okay, this is laminar. Definitely, if you move your probe, let's say, toward the wall, the flow would go down. As we derived earlier, toward the wall, velocity is slower. But still, it is straight line. Okay? But if you increase the flow rate further so that Reynolds numbers increases greater than 2100, you enter the turbulent region. The level of this flow rate would go higher because you apply more flow rate, right? At some point, when you reach the turbulent region, what you have is something like this. It's changing with respect to time. It's not a straight line anymore. Okay? But in general, you can still draw this line. This is average velocity for turbulent flow. And on average, this velocity is constant. That means it can be considered as steady state. So it is steady in general, in big picture, but in small time windows, you can see fluctuation. This is definition of turbulent flow. Okay? So in chapter 5, the blue line is actual velocity. The red line is called average velocity, and it will be average with respect to the window of time. So V bar, the average velocity, can be calculated by integrating actual velocity with respect to time. And then you divide it by the length of time that you consider. Let's say that you consider this period of time. The middle is called T0. I'm sorry. The width here is called T0. Okay? So if I integrate it from T minus half T0 to T plus half T0, that means I'm integrating within this window, finding the average number. Okay? This is the definition of what we call time average velocity. Of course, if you apply time average velocity to laminar flow, you end up with single constant number. If it is turbulent flow, however, the function is random, so this number would be very difficult to find. Okay? Now, the deviation from the average value to actual value represent fluctuation itself. Okay? So if you replace this velocity, it's essentially V bar plus fluctuation. Right? This fluctuation can be positive, that means it's higher than average velocity. It can be negative, that means it's lower. Okay? So if you split this into two parts, the first would be the integration of the average velocity itself and the integration of fluctuation. This is how we find the average. If you take a consideration, this is average of average. This whole term is basically average itself. Just like when you take average of lamina, it will get the same value. So this first term is the average of red line. So you get the red line itself. This second term is supposed to be 0, right? Because left-hand side of this equation is V bar. This term is V bar by definition. So this term, mathematically, it must be 0. So the equation tells you that even though the actual velocity is fluctuating, but on average, if you combine all the fluctuations together, it would eventually cancel out. That's how you get steady state condition. Understand? This term will be eventually added to the equation that we already derived, like equation of continuity, equation of motion, Navier-Stokes equation. So if you add this term into that equation, then you can get the set of equations that you can use for calculation of turbulent flow. That will be in chapter 5. So in order to move from laminar flow to turbulent flow, basically you just add this term, the turbulent flow or the fluctuation term, into the equation. Then you can have a new set of equations to solve the same thing. What you get from those equations is basically velocity profile in the same manner as what you did in laminar flow, except that in this case, the velocity profile that you will get would be the profile of the average velocity. So it will be the profile of the red line. Okay? Understand? All right, I give you a couple minutes just to make sure you get this point. Then we will move on to chapter 6. Okay? So let us move on to chapter 6. Now, chapter 6 is something that we will consider at the interface. Okay? It's the link between microscopic balance. Chapter 2 and 3 consider balancing around the shell, which is microscopic balance. After you integrate that shell, you get velocity profile for the whole system. Okay? In unit operation 1, or in fluid mechanics that you learned so far, you balance from in and out. That is called macroscopic balance. Okay? If you consider flow in the pipe, you can get, after you do the input balance, in and out balance, or if you use Bernoulli equation, you can get pressure drop. You can calculate pressure drop in the flow in pipe. And that pressure drop, in order to find pressure drop, you have to calculate friction loss. Remember friction loss? The F factor. Okay? In this chapter 6, we will link what we obtain from microscopic balance to macroscopic balance. In other words, this chapter 6 defines how we can calculate friction factor. Okay? So essentially, friction factor can be derived or can be calculated microscopically and then applied to macroscopic balance. I will show you how to do it in chapter 6. All right? Example that we will use is just a simple flow in the pipe. This example has I show you in chapter 2. During that time, we set up a shell. We end up with velocity profile. Okay? I also show you how to do it using the equation in chapter 3. You end up with the same velocity profile. This is what you got. From this, you see at the center, at r equal to 0, this term will be gone. The rest will be what we call maximum velocity. So maximum velocity can be found here. Okay? Then, if you take the average of this velocity, you integrate it across the surface area, divided by the, integrated across the cross-section area, and divided by area itself, you can get average velocity. And eventually, you see that average velocity of the flow in the pipe is half of the maximum velocity. Okay? Now, if instead of asking you to define or to derive velocity profile, if I give you this velocity profile, okay, can you find shear stress? Can you do it? In chapter 2, we start from shear stress and then integrate shear stress to get velocity profile. So if the velocity profile is given, then in order to get shear stress, it's basically differentiation. It's in reverse. Okay? According to Newton's law, as I said, Newton's law is the only equation that links between tau, that is what is transferring, with respect to velocity, which is what can be measured. Okay? This is Newton's law for this particular case. Of course, Newton's law is longer than this. But under this circumstance, you eliminate all terms that are 0, you end up with this equation. Right? You can see that it is linking between what is transferring with respect to what can be measured. So if velocity profile is given, in order to find tau, basically you just differentiate it, much easier than integration. Okay? If you take this, differentiate it, you end up with P0 minus PL over 2LR, which is supposed to be the same as what you will find if you start from shell balance. Okay? Now, if I want to find force that fluid is acting on the wall, okay? So Fc acting on wetted surface is essentially shear stress multiplied by area. Shear stress, by definition, is force over the area, right? If we want a force, you just multiply by the area, or you can basically integrate it over the area. In this case, we want to find force that fluid acts on the wall, so we have to limit tau to be at the wall, okay? And the area is supposed to be area of the wall. So the area of the wetted wall is basically 2 pi r times L times tau at the interface, which is at r equal to capital R. This would be force acting by the fluid to the wall. Okay? So 2 pi RL times tau, you just replace this small r into capital R. And we will call this one to be Fk. Then these are combined. You get pi r squared. These two cancel, L cancel. And you end up with delta P. Okay? You can also get this by doing the force balance over free body diagram of water. I showed you that already earlier. Now, here's the definition. The force is equal to A, K, F. A here is called characteristic area. K is characteristic kinetic energy. This small f is called friction factor. Okay? This probably will be the only equation that you have to remember. It will not be available in the examination room. But anyway, the examination is open book anyway. So in this case of the flow in the pipe, area, characteristic area is the area associated with solid and liquid. In other words, it will be wetted area. Okay? So wetted area in this case is 2 pi RL. Kinetic energy, characteristic kinetic energy is basically 1 over 2. Instead of mv squared, it will be kinetic energy per unit volume. So per unit volume, mass over volume is density. V squared, in this case, we will use macroscopic balance. So this velocity would be average velocity instead of local velocity. So this will be average velocity squared. You average first and you square it later. Okay? So if I take this equation, Fk equal to AKF, let me rewrite it this way. If I replace Fk from what I found over there, that's pi r squared P0 minus PL equal to A, which would be 2 pi RL times K, 1 over 2 rho V squared times F. Okay? If I rearrange the equation, I get F equal to 1 over 2 capital R over L P0 minus PL over 1 over 2 rho V squared. If you change R into diameter, this will be 4. So 1 over 4 diameter over length, and this term, which is exactly the same as what you learned in unit operation 1. This is called fanning friction factor. It is friction factor according to the flow in the circular pipe. And this is for smooth pipe. Okay? Now we know that earlier from microscopic balance, average velocity is half of the velocity max. And velocity max is basically P0 minus PL R squared over 4 mu L. So if I split this, or if I change capital R to D, this would be 4, okay? So if I expand the term, 1 over 4 D over L, I keep pressure to be the same, 1 over 2 rho. Now, this is V squared, square here, okay? If I take one V here, another V out, and this V will be replaced by this, okay? So 1 over V, which is 1 over 2 P0 minus PL over 4 mu L R squared. Of course, R squared is D over 2. So this must be square, okay? And you see that this pressure difference would cancel out. Eventually, I have mu here as the denominator of denominator, so it flips upward. You have mu up front. This L and L cancel out. Okay? I have rho V underneath here, so rho V. I have D here, 1D. This is D squared. This is single D. Cancel out. You get 1D left. All right? The rest will be number. 2 and 2 will be 4. 4 and 4 cancel out. I have 4 here, and I have 2 squared, which is also 4 here. So 4 and 4 will be 16. So 16 as a denominator of denominator is flipped out into 16 up here. Okay? So from now down here, you can see that this is what would be very familiar. Rho dV over mu, that's Reynolds number. Okay? So at the end, you get 16 over Reynolds number as a friction factor for the flow in the circular pipe and the smooth pipe, just like what you learned in unit operation 1. You can approximate friction factor from this equation as long as the flow is laminar. So this is basically the link between what you have used in unit operation 1. This is how it was derived. So imagine if the system is not circular flow, flow in circular pipe. If the system is more complicated than that, then you just repeat what you do or what you did in chapter 2 to find velocity profile. From that velocity profile, find the shear stress. From shear stress, locate the shear stress at the wall and plug into this equation, rearrange it again. You end up with equation for that specific system. So that's how we calculate friction factor. Just like the friction factor in the elbow, that will be calculated in the same manner. Okay? You have used this without knowing the source. Now you know it. Any question? So the rest is chapter 7, which would be macroscopic balance. It is exactly the same as what you used in unit operation 1. Basically, if you integrate this from microscopic balance to macroscopic balance, if you consider momentum only, you end up with Bernoulli equation, the famous equation that you have used so many times. Okay? Question? So we finished chapter 4, 5, 3, 4, 5, 6, 7 today. Very quickly. And that's the end of the first part of momentum balance. Next week, we will start energy balance. Okay? We will start next chapter of transport phenomena, which is energy section. Okay, if you have questions, please come and ask. Otherwise, you can go for another class.